Hey MathHL, so in this video we're going to look at how to find the intersections of lines that are in vector form. We're going to do this with both 2 dimensions and with 3 dimensions. So let's consider the possibilities of what can happen when we consider 2 lines. If we have 2 distinct lines, they can either be parallel, so they will not intersect at all, they will have the same slope the entire time. Coincident is when they have the same slope the entire time, but they also are basically just the same line twice. So that's coincident. We're going to look at in just a second how to tell the difference between parallel and coincident when you have the equations. The other option is that your lines can be intersecting. And in that case, we're going to find where do they intersect. So we will find the location of that point. Those are the 3 different things that can happen when you have 2 lines in 2 dimensions. So let's take a look at that a little bit. Here's just another explanation of coincident lines. Coincident lines and parallel lines both have proportional direction vectors. It's just that coincident lines are basically on top of one another, whereas parallel are traditionally what we understand as parallel. But the position vector that you have for your line will be either on both lines or they won't. Like, for example, if I consider this to be one of the position vectors, like one position on that line is that pink dot is not also on the other line. It's only on the top line. This pink dot is only on the bottom line. Whereas with coincident lines, the pink dot is on both. And that's basically how you tell the difference between parallel and coincident lines. As you figure out, is the point you've got on the other line? So let's take a look at actually the algebra behind doing that. So we are going to figure out whether the 2 lines R1 and R2 are parallel or coincident. Now, notice that they both have direction vectors that would simplify down to the same thing, or we can think of them as scalar multiples. If I multiply by 3 by negative 2, I get negative 6. Negative 1 times negative 2 is 2. 2 times negative 2 is 4. So these direction vectors are scalar multiples. That means that we know that these vectors are either parallel or coincident. So notice this is a 3-dimensional example. How you figure out coincident with 2 dimensions or 3 dimensions is the same, so it really doesn't matter. Now, what we do to figure out are they parallel or coincident is we take one of the points and we substitute it in to the other vector equation, and we see what happens. So if I substitute 4, negative 5, 7 into R2's equation, we can solve to figure out what t is. And if t is a consistent value for our x, y, and z components, then that means that they would be coincident. So, for example, if I solve the parametric x equation for t, I'd add 13 and divide by negative 6, so I would get negative 3. If I did the same thing with the parametric equation involving y, and I subtracted 2 and divided by 2, I would get negative 3 again. If I did the same thing with the z component, added 5 and divided by negative 4, I would again get negative 3. Since all of the t values are equal, these would be coincident. If one of the t values had been different, like what if this one had turned out to be 2, that would mean that the lines are parallel, meaning they have the same direction vector, but this point is not on this line. And coincidentally, this point is not on this line. It doesn't matter which way you do it, the result will turn out the same. Okay, so how do we figure out if two lines do intersect? How do we find out where that spot is? Well, in 2 dimensions, you've done this before, except usually we write our equations y equals mx plus b, then we set them equal and solve, or some version of that. But we're going to practice how you would do this with vectors, because how we do this with 2 dimensions and 3 dimensions can be the same. So you can do it the old-fashioned way. You could get y alone here. You could turn this into Cartesian form and get y alone, and then set them equal. That will totally work. But we're going to do this using kind of like a vector approach. First of all, what you want is you want to have them in parametric form. So it's awkward when they write your vector lines like this, but sometimes instead of writing a vertical matrix like this, they will write it in this form. So this is the position vector 2, -5, and the direction vector is -1, 3. So my x is going to be 2 minus 1 lambda. That's my x. And my y is going to be -5 plus 3 lambda. Now, what about finding our values in parametric form for our equation of our line in parametric form for the second one here? How we do that is we set it equal to some parameter. We already used lambda, so we want to use a different one. So I'm going to use k. You could use t. Basically, just don't use the one that was used for the other equation of a line. You want it to be a different parameter. And so now we're going to get x alone and y alone. Okay, so I'm going to get x alone. So I'm going to x equals 3k minus 2, and y equals -k plus 1. So now I have my x here and my x here. These are the x values for my 2 separate equations of lines. If they are going to intersect, that means their x values will be the same. So you're going to take your x equations and set them equal. 2 minus lambda equals 3k minus 2. Now you're going to take the y equations and set them equal. Notice now we have 2 equations and 2 unknowns, so we'll simply solve this as a system. So I think I'm going to multiply the first equation by a 3. So I'll get 6 minus 3 lambda equals 9k minus 6. And I'll just rewrite the other equation and add straight down. So I'll get 1, my 3 lambdas cancel, equals 8k minus 5. So I'll add that over. 6 equals 8k. So I'll get that k is 3/4. Okay, now I need lambda. Actually, I don't need lambda. Now what I need to do is plug that value in to the x and the y components and figure out what the point of intersection is. So these lines intersect at k equals 3/4. By plugging into k, I can find the exact x and y values. So I just plugged them into each of those. So, oops, this is supposed to say 3/4. So I'll get 9/4 minus 2, which is 1/4. And here I'll also get 1/4. -3/4 plus 4/4 would be 1/4. So these 2 lines intersect at the point 1/4, 1/4. That's the same thing you would get if you got y alone here. If you wrote this in Cartesian form and got y alone and set them equal, it'll be the same solution. This is just a more vector approach to that situation. It's also the approach we're going to use with 3 dimensions. And that's what's most important, is because we have to use this approach for 3 dimensions. Let's get into that. For 3 dimensions, Two distinct lines can either be parallel, parallel, coincident, intersecting, or skew. Parallel coincident, the way you deal with that in 3 dimensions is the same as you deal with it in 2 dimensions. In fact, our example was in 3 dimensions. You see if their direction vectors are proportional, and then you see if this point is on this line or if this point is on this line. If it is, then they're coincident. No, then they're parallel. But 3 dimensions has this extra option of skew. That's where you have 2 lines that would never touch because you're in 3 dimensions. These intersect, skew. Intersect, skew. We need to know the difference between those. So let's look at how we do that. So we got our problem here. Determine whether each set of lines in 3 dimensions are intersecting or skew. If intersecting, find the point of intersection. So the first thing we want to do again is write these in parametric form. So we're going to pick some parameter to set these all equal to. And they need to be different for the 2 lines. So they can be lambda and k. I think that's what we used on the last one. They can be s and t, whatever we want to use. I think I'm going to use k and t. Okay, so now for line 1, let's write these in parametric form. So if I'm getting x alone here, I have x minus 1 over 2 equals k. So x would equal 2k plus 1. Y, I'm going to have y plus 1 over 3 equals k. So I'll times the 3 over and subtract a 1. And then lastly for z, I have z minus 3 over 4 equals k. So I'll times the 4 over and add 3. Okay, so that's for line 1. And now for line 2, we do the same thing. So for my x component, times the 2 over, subtract 1. For my y component, y just equals t. And for my z component, times the 3 over, add 1. Okay, so I have my parametric equations for both line 1 and line 2. So now we want to figure out what k and t are. Similar to what we did in the last one, we figured out what k was. Notice last time we did not find t. We did not, or lambda, sorry, the other parameter was lambda last time. Last time we only found one parameter's value, k. This time we actually have to find both. For 2 dimensions, you only have to find one. For 3 dimensions, you have to find both. Well, how do we do that? Well, if we think about setting our x's equal and our y's equal, we can do the same steps we did last time in order to find k and t. But notice we didn't use all 3 sets of equations. We only used x and y. That's going to be important later. We're going to have to deal with z later. But first, let's just solve this system here. I'm going to multiply this by negative 2 so that the t's will cancel. So I get negative 6k plus 2 equals negative 2t. So I'll have negative 4k plus 3 equals negative 1. Subtract the 3 over and divide by negative 4, so k equals 1. Okay, so k equals 1 on that. Now I need to find t. So I'm going to plug k equals 1 into one of these. So t is 2. Okay, now what you do is you plug these into both sets of parametric equations. Both sets. Well, you plug the k into the k and the t into the t. On the 2-dimensional problem, we only plugged in one. We only found k and then plugged it in. There's a reason why we have to plug in both this time, and we'll talk when we get there. So I'm going to plug k equals 1 If we want to write this in vector form, we totally can, or a vertical matrix form. Okay. So I just switched it from parametric to vertical matrix. And now I get the XYZ. Let's see, 1 plus 1 times 2, so that'd be 3. Negative 1 plus 1 times 3, so that'd be 2. 3 plus 4, so that'd be 7. So the point on line 1 associated with k equals 1 is 3 comma 2 comma 7. Let's do the same thing for line 2. So I'm going to take XYZ equals negative 1, 0, 1 plus T 2, 1, 3. Okay, so now I'm going to plug in T equals 2 there. And I'm going to see how that turns out. So I get negative 1 plus 4, so 3. 0 plus 2, so 2. And 1 plus 6, so 7. So you'll notice that I got the same result twice. And you're like, well, why would I do it twice if I get the same result? I'm wasting my time. Here's what might happen. Your X and your Y. When you plug in k equals 1 and t equals 2, your X and your Y will match, guaranteed. But Z is not guaranteed to match. What was different about Z that would make that exception? Why would X and Y definitely match, but Z might not match? Because to get K and T, we only use the X and Y equations. We never use Z. So the one parameter you don't use, like the one component you don't use, whether it's X, Y, or Z, that's the one that could end up being different. And that's what determines if they're parallel or not parallel, intersecting or skew. So because it turned out the same for both, they are intersecting, and they intersect at 3, 2, 7. You can probably anticipate what's going to happen on the next example. It's not going to match. The two X and Y might match, but the third one, Z, maybe won't. So let's go through that and see what that experience is like, what it feels like having that happen. Okay, maybe pause the video and give this one a try without watching, and then you can see if you get the right result in the end, the correct values and everything. Okay, so I need to turn this into parametric form. I'll use the same parameters as last time. I'll use K and T. So for the X component, I'll need to times 3 over and add 2. For the Y component, I'll times the 4 over and add 1. And for the Z component, times the 2 over and subtract 1. For line number 2, I'll multiply 2 and then subtract 1. For Y, I'll multiply 3 over and add 2. And for Z, I'll subtract 5. Okay, so now I pick 2 of my components, either X and Y, Y and Z, or X and Z. It actually does not matter. So sometimes I'll think about which ones might be easiest to get to cancel. Like, he's standing out to me because the T doesn't have a coefficient. So I think I'm going to use the Z variable and make that one of my equations to solve. And then maybe the X variable and use that as my other equation to solve. So you only need to pick 2 of them because you only have 2 parameters, K and T. So Y is the one that might be different this time. Okay, let's solve for K and T and see what happens. So I think I'll times this by negative 2. Keep this one the same. So I'll have negative K plus 4 These canceled, equals 9. So negative k equals 5. So k equals negative 5. And then we can do the same thing with, sorry, not the same thing. We'll plug in k to figure out t. I'm one step ahead of myself. So I'll get negative 15 plus 2, so negative 13. So negative 12 when I add. So t is negative 6. Okay, so now that I have my parameter values of k equals negative 5 and t equals negative 6, I will plug those both in and see what point I get for each line. So for line 1, I'm going to get 3 times negative 5 plus 2, 4 times negative 5 plus 1. So this time I just wrote it in parametric form instead of vector form. Either way, you'll get the same answer. Who really cares? And then 2 times negative 5 minus 1. So I get negative 13, negative 19, and negative 11. Okay. So now I want to see what happens when I substitute those into line 2. So I'm going to substitute negative 6 into line 2. So here I'll get negative 13. Here I'll get negative 16. And here I'll get negative 11. Notice the x's matched, the z's matched. That's because we use the x and z equations to find k and t. And then the y's don't match. Since the y's don't match, these would be skew. That's what determines whether they're intersecting or skew, is what happens with that third variable, the variable you did not use in your system. So this issue only comes up with 3 dimensions, not in 2. So in 2 dimensions, you only have to find the value of one parameter, either k or t, and then plug it in. But when you have 3-dimensional, you have to find k and t, plug them in, and see if all 3 components end up the same. And that's how you tell if they're intersecting or if they're skew. Okay, that wraps up this video.